My name is Sebastian Alberternst and I'm from the German Research Center of Artificial Intelligence in Saarbrücken, Germany. This presentation is split into two parts. The second part will be held by my colleague Adrian Takli. In this talk, we are going to present our approach for a cloud-oriented management of AI-based IoT devices and services. Starting point is the proliferation of various IoT sensors and devices, especially in smart environments. These devices make a large amount of data available and therefore provide the opportunity to process these data with the most advanced artificial intelligence techniques. In particular, machine learning-based techniques for developing value-added services. On the other hand, these environments and domains call for knowledge-driven approaches, leveraging pre-existing knowledge. Our goal is to combine classical symbolic AI and advanced machine learning approaches. In order to achieve this, the key idea is to make applications at the various levels accessible in a transparent and uniform manner by providing access to federated clouds, local clouds, and environments. Several problems have to be tackled. There is a need for uniform access, secure management, and orchestration of IoT-related software and services. Devices have to be described and managed in a uniform way. We developed a thing registry for resource and data collection based on W3C standards. Usage of semantic web technologies and agents for orchestration. We start with introducing some preliminaries and then present the approach for the thing registry. For orchestrating services and devices, we use the agent platform Arjan developed at the DFKI, which we present in the following. We illustrate our approach with a use case from an assisted living scenario. But first, we want to take a look at the prerequisites of our approach. Our approach uses the W3C Web of Things architecture, which contains several building blocks in order to improve interoperability and usability across IoT platforms and application domains. The key application of a Web of Things architecture is the thing description. It describes metadata and interfaces of things like properties, events, and actions. It's considered to be the entry point of a thing, much like an index.html file for websites. A thing description describes its interfaces and metadata using JSON-LD to combine JSON with semantics, making it possible to add context knowledge from other namespaces to integrate additional semantics to the content of a thing description. Another prerequisite of our approach is Sense Web of Things, which was developed in the Sense project, which focuses on interoperability and smart building. It adds 3 additional building blocks to the Web of Things architecture with the aim to support common problems when working with things, as well as increasing the interoperability. The location of things is a very important property in order to build use cases. For example, to find functionality in a specific room of a building. Machine learning in smart home environments is becoming increasingly important. Developers may want to find time series values for a specific property of a sensor in order to develop machine learning models. Sense Web of Things describes time series interfaces directly in the thing description. An additional building block is the payload mapping. Developers may want to map payload between heterogeneous devices automatically. The thing registry is the central entry point for developers to find functionality and data. It is responsible for discovering and generating these thing descriptions and storing them, thus making them centrally available. Multiple instances of thing registry can exist on the cloud levels as well as on the edge levels. The 4 main tasks of the thing registry are discovery, security, querying of metadata, and exposing things. We thereby provide a decentralized data sharing and processing architecture for data spaces, including secure data access, which is currently a central aim of the European Gaia-X initiative. The discovery is responsible for generating thing descriptions for legacy devices, which are devices that don't provide their own thing descriptions. It can be extended via plugins in order to be able to discover and generate these thing descriptions based on templates, which means it can easily be extended to discover devices from a multitude of manufacturers. On the other side, the registry supports discover mechanisms in order to get discovered by other services and devices in a local environment, like DNS service discovery. The registry integrates various security mechanisms like authentication, authorization, and encryption. An identity and access management solution is integrated into the X registry to provide authentication via the OAuth 2 protocol as well as authorization of the resources via the user-managed access protocol. We support authorization down to the level of affordances, meaning actions, properties, and events. For example, a user can share the battery status of a sensor with the facility manager, but not the sensitive data of the sensor itself. We also support encryption via the transport layer security. Another role of the registry is querying of metadata. We provide multiple interfaces to query metadata, which helps developers and users finding functionality in data. For example, finding all temperature sensors in the kitchen or a brightness sensor in the bathroom. We have 3 ways of querying data using the information model: JSON-ATA, JSON-Path, and JSON-LD framing. Additionally, we support Sparkle endpoints for querying data based on the semantics, which gives users the possibility to focus more on the things they want to know instead of how the data is structured. A reasoner is also attached to the Triple Store where all the semantic is stored, which helps to increase interoperability across ontologies. The last task of the thing registry is exposing things. Working with many different thing descriptions can be quite complicated for developers. A developer has to manage all the different credentials and support various protocols and payloads described in the thing descriptions. The exposing thing mechanism of the registry tries to solve this problem by automatically generating a homogeneous thing description. Different protocols like MQTT and CoAP are, for example, mapped to HTTP where possible. Additionally, payload mapping is used to map various payloads to one homogeneous format, which we will see in the next slide. The payload mapping approach tries to solve the problem that things have various payloads formats. It makes it hard to exchange data between multiple heterogeneous interfaces. The goal is to allow communications between arbitrary services by mapping payload. Our method lifts payload to a semantic representation using RML mapping by using our developed lifting service. After that, the semantic data representation is lowered to the target interface structure using the semantic description of the target API. We now have the possibility to describe and discover things, homogeneously expose them across multiple protocols and payloads, as well as securing them. When developing new use cases, developers want to find functionality in things across multiple clouds, as well as the exact opposite, securely deploy services in a trusted environment on the edge. By providing semantics on the cloud level, developers are able to search functionality across multiple clouds. For example, a face recognition service that is running in a specific country, providing certain security capabilities for a certain price. The developer wants to combine the face recognition with things from the user, for example, the front door camera or a smart lock. Our approach combines the International Data Space Information Model with thing descriptions. The IDS information model is an ontology defining the fundamental concept of data spaces, their interactions, the resources exchanged by them, and data usage restrictions. By combining them with thing descriptions, the developer also gets a description on how to use the services in the cloud. When orchestrating services across multiple clouds, identity management plays a central role. Federated identity management is necessary so that users can use the identity across multiple trusted systems. Exposing things to the cloud is sometimes not possible due to security restrictions. Maybe the user doesn't want to send video streams to the face recognition service in the cloud, even though the data is encrypted, because he ultimately cannot trust the service. The user loses his data sovereignty as soon as the image from the camera entered the face recognition service. Rather than using a service in the cloud, a developer can spawn an isolated instance of it on the edge, for example using the IDS Trusted Connector, by providing additional information in the thing description on how to spawn an isolated instance of a service in a trusted environment. As shown, semantics are used on multiple levels: searching for functionality across clouds, spawning isolated services in a trusted environment, describing how to use and interact with services, and describe and map payload between things.
All right, thank you very much, Sebastian, for the first part of our presentation. Now I will continue with orchestrating things and services. So the multi-agent system paradigm is predestinated to orchestrate the presented distributed services and semantic descriptions, and thus to realize a higher level intelligent functionality. By distributed agents interacting with each other and accessing, for example, real-time data of a building, an abstraction layer is introduced that hides the complexity of the environment from the user. This is one of the reasons why multi-agent systems has been used in the Web of Things in the past. A software agent usually has the architecture shown on the left. In order to interact with the agent's domain, an agent has sensors and actuators. In order to execute actions based on the perceived data, decision-making is required, which is executed based on agent goals to be achieved. To implement a multi-agent system in the presented environment, we use the framework Arjan. An Arjan agent has the properties described earlier, with the sensors and actuators being individual linked data resources in the distributed domain. For example, a smart plug or internet-enabled socket with the associated thing description could be used or could be such a sensor. The agent model with the knowledge base, but also the decision making on the agent behavior, are completely represented in RDF in Arjan. The behavioral model used in the Arjan framework are behavior trees extended with Sparkle queries, but can be augmented with other AI methods as well. Further, Arjan provides a web editor for modeling and is open source and available via GitHub. As mentioned, the behavior tree paradigm is used for decision making and behavior execution in Arjan. A behavior tree, as shown, is executed in depth-first manner and is usually event-based. Branch nodes such as composite or decorator nodes are used for internal execution of the tree. Composite nodes, on the one hand, can be used, for example, to implement sequences or parallel executions. Decorator nodes, on the other hand, have only one child node, which, for example, is executed several times in a repeater node. The leaf nodes, like conditions, but also updates and actions, execute the emergent behavior in the end. These nodes access the knowledge base of the agent, for example, to query the current agent state via a condition, or to read data via an action in order to execute a resource capability. In Arjan, we use RDF triple stores as the knowledge base, which the nodes access via Sparkle. As mentioned before, the whole agent model, hence also the behavior models, are described in RDF. The left side shows a simple behavior tree graph with a sequence and a leaf node for evaluating incoming events. The corresponding RDF representation is again shown on the right. The colored boxes highlight the respective descriptions. So, how can Arjan be used for our purposes in our semantic smart environment? For example, we can implement a so-called monitor agent that uses the thing descriptions in the registry to read out the status of the corresponding resource periodically, in our case a smart plug, and updates the registry in this process. Since the thing data may be provided in a format other than RDF, this information may also be lifted into Arjan. Control agents, on the other hand, are extended in that they not only read the state of a resource, but also execute its available functionality. In the example, a controller agent could read the state of a smart lock via its thing description, open or close it based on the agent goal. This goal can either be fixed in the agent behavior, but a user could also communicate it to the agent. A behavior tree of a monitor agent is shown on the left. This tree is executed periodically, and the time span with which a resource is to be read depends on its thing description. After such a time period has elapsed, the respective resource is read via its RDF or Sparkle endpoint, and the received data is written to the registry. In order that a controller agent can be used intuitively by a user without knowledge of RDF, Sparkle, or behavior trees at all, we offer so-called templates via a web interface, which represents behavior trees and where predefined variables can be set. The graphic on the right shows such a template through which the user can define a sequence of switching a light on and off. Having introduced Arjan and how agents can be used to interact in our Web of Things domain, we now present a holistic example application. The presented architecture with the individual components is shown here. In addition to input and output devices or things, we also listed services that can be embedded in the overall system via their thing description. Furthermore, the thing registry is presented as the most important component, which is accessible via HTTP or WebSockets and RDF and Sparkle in the distributed system. It holds, as already mentioned, all connected components and their thing description, and serves as a central point to interact with the overall environment. Furthermore, AAM instances are available for secure access management and Agent agents for creating higher level functions. Now let's look at our use case scenario. We assume a house that is equipped with things like smart plugs, machine learning service and smart devices, and connected to the thing registry where all services run in federated clouds. In this house lives a person who interacts with things, and thus her activities are communicated to the overall system. Machine learning services are used, for example, to detect movements or to derive activities based on power consumption. Furthermore, Agent agents are included that periodically query device information but also receive activities and react to them independently. If an inactivity of the resident is detected within a defined period of time by an Agent agent, the agent should initiate further steps to provide assistance to the responsible care person in question if necessary. One possibility is to notify a contact person who will then be granted access to the house via a smart lock so that they can check on the possibly endangered person. In order for the agent to gain access to the resident's personal data in advance, the resident must grant the agent access via an AAM instance. Not only does the agent need access, but the individual things or devices in the house needs it as well. If the resident or the installer of the semantic system has given the release, the agent now has access via time-limited token to the real-time data of the individual thing, but also to further services for activity recognition or for communicating with third parties, for example, the responsible contact person in our scenario. Since the agent now has access to all relevant data, it can listen for incoming detected activity. Possible activities are, for example, a person getting up or boiling water. If an activity is received, a timer is reset, the agent knowledge is updated and further listened to. This timer can be set to 2 days, for example. This means that if no activity is detected for 2 days, a malfunction must be assumed. If this is the case, the agent tries to access real-time data of the motion detector directly. If still no activity is detected, further steps must be taken, which are explained in the following. In the first escalation stage, here marked via number 1, the agent first tries to contact the resident via a mobile app to ask about their condition. How to contact that person is noted in the registry and enabled for the agent. If a negative response is returned or a timer has expired, the next step, number 2, is executed. In the second escalation stage, a contact person is alerted via a so-called community platform, which is also activated for the agent. This person can now independently try to contact the resident. And last but not least in our scenario, if the contact person wishes to visit the resident in their home, the agent can unlock access to the home for the contact person in advance by using face recognition plus a smart lock for this purpose in step number 3. Now to conclude our presentation, we come to a brief comparison of our work with existing systems and a summary. Basically, services are already available that use the W3C stack to manage distributed systems. These usually consider only one aspect, and that to a limited extent of the overall system presented here. If agent systems are considered in this context, they have been used since the time 0 of semantic distributed systems. To control these, of course. But Agent is, to our knowledge, the only agent framework that uses the W3C stack so consistently and embeds itself natively into a linked data or Web of Things environment. Now to the summary. We presented an approach to address evolving cloud to things continuum with a thing registry and an agent-based orchestration framework, which we combine to support semantic orchestration of IoT use cases in the federated cloud environments. We have illustrated the approach with a use case from an assisted living scenario. Obviously, the IoT ecosystem is currently growing at a rapid pace, so ongoing developments will continue to be monitored and taken into account. So that's it. Thank you very much and goodbye.